In this video, I'm going to do some of the problems from section 8.2. Now, sorry for any confusion, or not confusion, but just pain in the butt that this causes. There's a video that I made that has the solutions for what I thought were the harder problems. Not to say that there's anything wrong with coming and looking at these, but there's a video that has let's see, I guess it has numbers 11 and 13 and 17 and a couple of the maybe 33 and 34 or something, 32 and 33, something like that. So those are in a separate video, and I'm just going to do these ones here. Talking about integration by parts. So there's two different things that we need to know about integration by parts. Two different methods, I think. First of all, the guiding principle here is this little acronym, LIATE. Do you know the difference between an acronym and an initialism? I probably told you this in some other notes somewhere. An acronym is called an acronym if you pronounce those words. So I say LIATE here, so this is an acronym. But if you have something like the CIA or the FBI is an initialism, not an acronym, because we don't call it the FB or FB or whatever. We just say the letters, so that's an initialism. This is an acronym, LIATE. What does it stand for? This is log functions, inverse trig, algebraic, which is like polynomial type things, regular trig, and exponential functions. So this is our little guiding thing. If you have either of these involved, the Li, then that's going to make you have to do full-on integration by parts, which is the integral of u dv is equal to uv minus the integral v du. Remember, this is just sort of a rearranged, integrated version of the product rule. That's where this comes from. Now, if you only have the ATE involved, then probably you can do the tabular integration, right? Where you pick your algebraic to go here, and your trig or exponential to go here, and you find derivatives here, and you find antiderivatives here, and you play that little tic-tac-toe game. So there's two options for what to do, but you don't really get, I mean, you can always do this, but if it's possible to do this tabular thing, you definitely want to go with that. All right, that's a quick review of that. You already have that from your notes, so I guess I'm just getting myself warmed up there, here, everywhere. So the first one, I have x times e to the negative 2x. That is algebraic x and exponential e to the negative 2x. So I'm going to do this. So I have x e to the negative 2x. So my derivatives are 1 and 0. My antiderivatives, be careful, you're taking antiderivatives. Antiderivative of e to the whatever is e to the whatever. That's just a constant, so I just have to divide by that. And then I have to divide by it again. And then I play ticky-tacky-toe, and these change signs on me, they alternate. So that's going to give me an antiderivative of negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. And these are just general antiderivatives, so I should be tacking on a plus c. And that's it. It looks kind of crazy, but to calculus students with all of the experience that you have, it's really not actually very hard to do that. Just have to be careful, right? There's details that need to be managed properly. Okay, let's do number 3. It looks like another x squared and e to the x. You know, I don't, this little table thing that I drew here, I think I'm not crazy about that because I didn't like the way I had to draw that. I hadn't made one of these in a little while, so I think I'm going to not do that table thing and just take my derivatives here till I get 0. And then take my antiderivatives here, which are just all e to the x. Don't forget to play the switching signs game, plus, minus, plus. So let's see what we have here. My antiderivative is x squared e to the x minus 2x e to the x plus 2e to the x. I think this process, this whole little tic-tac-toe game, it's kind of like this process is to integration by parts as synthetic division is to like polynomial long division. It's just a shortcut. It accomplishes all the right things in an efficient algorithm. All right, x and sine x. I'm still in, or sine 3x rather, I'm still in the ATE, the ATE type of problems here. What's the antiderivative? Be careful with here. We're taking antiderivatives. What's the antiderivative of sine 3x? Antiderivative of sine is negative sine, negative cosine rather. And then there's a 3 in there, so got to do that. And then the antiderivative of negative cosine is negative sine, and I'm going to have to divide by that 3 again. Right? Easy to make SIGN sign mistakes here. All right, so let's see what we have here. I got minus 1/3 x cosine 3x. Minus times minus is plus 1/9 sine 3x plus c. Number 7, I got algebraic and trig again. X squared and cosine of x. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine. There was nothing inside there, so I don't need to mess with constants in front. Okay, so I got x squared sine x plus 2x cosine x minus 2 sine x plus c. Right? If you're looking at this and saying, wait, hold on a second, you're telling me that this is the antiderivative of, what was the original, x squared cosine x? That means that if you took the derivative of this, you would get just the one term x squared cosine x. And we look at this and like, how the heck was that? How would that happen? Well, it's kind of cool to see how it actually plays out. So I dare you right now, if you're looking at this video, checking your answers here, to take the derivative of this very carefully using the product rule, right? That's a product, and that's not. Using the product rule, take the derivative of this and see what happens. And you'll see the magic of integration by parts, how cool it is. I'm going to just look real quick at the answers to those 3 problems. Make sure I didn't do anything wrong. That looks good. And that looks good. The easiest thing to that can go wrong is to just mess up one of the plus-minus signs. But it looks like your calculus teacher is all right so far. So 9, 15, 29, and 31 now. Number 9, we have not algebraic and trig. Okay, so I need to think about my, just going to write down my Liate here. I have the integral of x natural log x dx. So the game here is, I'm going to set up my little table, u du, and then, v and dv. And what the Liate does for us is it tells us how to pick these things. What we need to do is, we know that this is the recipe, integral u dv is equal to u times v minus integral of v du. That's a thing you need to have memorized. This is what we're starting with. So I need to pick the u and the dv. And this tells us the order to pick them in. Whatever you come across first should be this, and whatever you come across second should be this. So let's see, I've got a logarithm, that's the first thing, so that's got to be here. And then this is algebraic, so that goes here. And whichever one goes with the dv, that takes the dx with it. Okay? So on this side, I need to take the derivative. Derivative of natural log x is 1 over x. Right? And since I don't have du dx here, the dx is going to pop up over here. It's not like a deal breaker necessarily if you forget these, but it's good accounting to keep track of them. And then here I need to take the antiderivative, that's x squared over 2. Okay, so what does the rewrite look like? So this is equal to uv x squared over 2 times natural log x minus the integral of v du. X squared over 2 times 1 over x, that's just 1/2 x. And that is something, the goal here is that when you do the rewrite, this is going to turn an integral that we couldn't do into one that we can do. So looks like we're good here. Antiderivative of 1/2 x is bump the exponent up 1 to 2 and divided by that, it's 1/4 x squared plus c. Now that is my answer. Just going to check that, make sure that we're all good. Yep. And 15, sine inverse of x. So this is one of those problems where you look at this and like, wait a minute, if this is supposed to have a u and a dv, there's only one thing here. So how is that supposed to work? Well, there's a few functions. The inverse trig and logarithms that work if you just, using this method, that work if you just take the dx to be the dv. I think you have that in the notes. I think I did an example of at least one of those. So we treat this like the inverse trig. And then we treat this just like 1 dx as the algebraic. Okay, so I need to take the derivative here. Derivative of sine inverse x is 1 over 1 minus x squared dx. And then the antiderivative of 1 is just x. So let's see where that gets us. It gets us back to uv minus the integral of v du. And then, how did that help? Well, actually, we can do this integral. It's its own separate problem. It's a little u substitution problem, but since I have an x to the first power here and an x squared inside here, I could say, let's let u equal 1 minus x squared, then d, not to be confused with these, this is a reset of this, just doing a u substitution. Now, du is equal to negative 2x, and if I need a negative 2x, if I need a negative 2 on the inside of this, then I would have to put a negative 2 on the outside, a negative 1/2, sorry, to balance that on the outside of this. And I already have a negative sign, so I have to clean that up here in a minute. So this hasn't changed. And here, negative, negative, so that gives me, oops, sorry, not supposed to be an equal sign there, plus 1/2 times the integral. And then here, I have my negative 2x dx, that's all du. And then I've got this underneath, so 1 over the square root of, that's u to the negative 1/2. So x sine inverse x. And then what's the antiderivative of u to the negative 1/2? Well, you bump the exponent up by 1 to u to the positive 1/2, and then you divide by that new exponent. And dividing by 1/2 is going to cancel out that 1/2. So I just end up with the square root of u, and u is this. And that is the answer. Let me just check that, and that's all good. So that's another one where you feel like, really? Like if you took the derivative of this, you're just going to get this? Yep. Go ahead and try it if you want. Next problem that we need to do is 29. Again, sorry if you have to skip back and forth between the two videos. Sorry, that's all I can say. 29, same deal, except this is a definite integral from 0 to 2. So how do we deal with that? Well, we just do the whole thing. We're just going to find that antiderivative, get it all the way, and then we'll set it up. So I'm not going to do anything different here. I'm just going to do my tabular thing because it's the right type for that. 1, 0. The antiderivative of this would be 1/2 e to the 2x, and then 1/4 e to the 2x. So the antiderivative of this is 1/2 x e to the 2x minus 1/4 e to the 2x from 0 to 2. So let's see, I plug the 2 in here, I get 2 times 1/2, those cancel out, e to the 4th. And then that's minus 1/4 e to the 4th. And then minus, plug in a 0 here, and there's an x there, so that all goes away. And then minus 1/4, and then that's e to the 0, which is just 1. So I think you need to be real careful about those signs, right? Easy mistake to make. So a whole e to the 4th minus a quarter of 1 is 3/4 of an e to the 4th plus 1/4. So that's fine. I suppose you could common denominator that and write it like that if you want. Let's see how they wrote it in the book. They went with this. All right. And then last one for this video, number 31. We've got x squared natural log x. So that is not going to submit to tabular integration. So I'm going to need my u du v dv. And what are my limits? 1 to e. 1 to e. So let's see. I have to pick the Lyautey. I got logarithm, so that's got to go first. And then my algebraic will go here. So the derivative of natural log x is 1 over x dx. The antiderivative of x squared is x cubed over 3. So the rewrite of this is going to be uv, it's x squared over 3, minus the integral of v du, which is x squared over 3. And what about these limits? Well, this part is already like the antiderivative, so for this part, if you wanted to just be really solid with your notation, I'd be plugging that in. I'm not going to do it yet because I want to do it all together, and then this part, I still have to find that antiderivative. So natural log x times x cubed over 3 is that part. And then the antiderivative of this is x cubed over 9. And now that I've got everything in antiderivative form, I can just do that for the whole thing. So for my my preferences of how you write things down, I wouldn't fuss at you if you didn't put the 1 over e at this stage and you just reattached it here. That's up to you. If you think that's a risky move for you because you might mess that up later, then do that. But I'm not going to plug these numbers in until I have the whole antiderivative. So that's how I'm going to manage that. Okay, so plugging stuff in. I've got natural log of e is 1 times e cubed over 3 minus e cubed over 9 minus, I plug a 1 in here, natural log of 1 is 0, so that term's gone, minus 1/9. All right. So let's see, if we wanted to simplify, that's totally fine. You could leave it like that. If you wanted to match it up with what's in the book, 1/3 is the same as 3/9. So 3/9 of one of these minus 1/9 is 2/9 of one of those plus 1/9. So I suppose you could do that to clean that up. And let's just check and see. Yep, that's the answer. All right.